All right. Hey, guys. I'm Teresa. Some of you might know me already as your TA. Others might not know me, but I am one of the TAs for Earth History. Okay. So today's lecture is about climate cycles. So this is basically describing the fact that the Earth's climate has a history of going from cooler to warmer periods in a fairly regular way. So we'll discuss today basically the factors that might be causing that kind of regular going back and forth between cooler and warmer time periods, and also think about how human activity could be impacting and interacting with that, that natural regular pattern. So why do we care? Hopefully you guys recognize that the Earth's climate has a massive impact on life on Earth. We've had ice ages where it gets very cold, greenhouse ages where it gets very warm, and these have impacted what species do really well, what species go extinct, where do these species exist? You can have palm trees at the poles if it gets warm enough, and you can have glaciers at the equator if it gets cold enough. But obviously, again, climate and how it's changed has massively, altered how life has evolved on Earth. And also for the modern day, if we want to understand how our actions today could be impacting climate, we would do well to understand how the climate changes just on its own. So we can isolate, okay, what's just the Earth doing what it's always been doing? What is us impacting it in some way? All right, so there are several factors that can influence Earth's climate, but they can be broadly boiled down to two big players that we'll discuss today. The first one is called astronomical cyclicity. This is basically talking about how, the Earth goes around the sun, the Earth is tilted, and those factors can change over time, and that can change how much radiation or sunlight or heat will hit the Earth and how it hits the Earth. So we'll talk about that in a couple slides. Second is the amount of carbon in the atmosphere. You guys might have already heard about this one, where if there's more CO2 in the atmosphere, more carbon, that generally leads to a warmer climate and vice versa. Okay? So before we get into all of that, we want to talk about the whole idea of cyclicity. So this is basically describing events that occur at a regular interval. So this can be anything that you want to measure. It can be temperature, which is the main one we're measuring today, or like how much CO2 is in the atmosphere, or anything else you want to measure. So when these have a cyclic nature, what will happen is you'll have some value at one point it'll change to a different value, and then go back to that same value, and then back to that lower value. So again, this could be temperature, could be CO2 concentration, whatever. And what you should be able to see crests and troughs. So like, peaks and valleys basically. And a cycle is basically saying, okay, pick a starting point, which is maybe a crest. How long does it take for us to get from, this crest all the way back to the next crest, or like from this value or this position or whatever, do some changes and then come back to that same position, that same value. That's a cycle. So for example, you will see this figure in your lab. This is not a perfect wiggle like the one we have here, but you can still hopefully see how there's like a really broad pattern of like kind of this reflectance. So decrease in reflectance, and then an increase, and then a decrease, then an increase. Here's our crests over here, right? And here's our troughs down here. So again, a cycle will be like, okay, how long does it take to get from, or how deep do you have to go in this case, to get from this crest to this crest, okay? So that's that broad idea. You'll get a lot of wiggles today. Just make sure you can find the crests or the troughs, and make sure you can measure how long it takes to get from one crest to the next crest. All right, so that's that part. So we're going to go into our first factor that can influence climate. Again, that's called astronomical cyclicity. All right, so there's going to be a couple main ideas you want to keep in mind. So one, this whole concept is, again, covering the fact that the Earth goes around the sun, the Earth is spinning on its axis, the Earth is tilting. You probably heard about all these things. But those processes are not, constant. They do change. They shift over thousands of years, and that can actually affect how much radiance or sunlight or heat will hit the Earth at a given point in time. Second thing to keep in mind, radiance is, heat, so more radiance, it gets warmer, less radiance, it gets colder. That should be pretty straightforward. Finally, keep in mind that, there are certain parts of the globe where if they get warmer or colder, they'll have a really big influence on how the larger climate goes. So basically, in this case, it's the poles. If the poles stay consistently cold over time, that will tend to lead to an ice age. Vice versa, if the poles get warmer over time, that tends to lead to a greenhouse age. So again, keep in mind for these next couple slides, what factors will lead to more or less radiance, more or less heat hitting the poles. The poles are the key thing in this whole idea. Okay, so there's three concepts we'll hit on, and then we'll bring them all together, hopefully. So the first concept is called eccentricity. So eccentricity is describing basically how circular is the Earth's orbit around the sun. So we can have a very low eccentricity, a very circular orbit. That's as you can see here. So basically that means at any given point in the year, this circle is our year, we will be more or less the same distance from the sun, okay? This is in contrast to high eccentricity or a more elliptical orbit, where that means that, again, this is 1 year. At this time of the year, we're pretty close to the sun, versus this time of year, we're further away from the sun. Now, important to remember, this could be winter and this can be summer. If we'll talk about this next, but the tilt is what makes seasons. This is just how close or far from the sun the Earth is. Okay, so again, this will change over time, and it will go from a more circular to a more elliptical orbit over time. So to help illustrate this, I have a little website here that I found that's very useful. All right, so this is a website. I will share the URL so you guys can look at it and play around with it and hopefully help you understand what we're doing here. So here's the Earth going around the sun. This is basically, we can have the current day and we can change the marker to go back in time, okay? So, all right, let's have eccentricity. We're gonna do for the top view because it's a little easier to see. So what you can do is you can go back in time and you can see how the Earth's orbit is actually slightly changing. It's very subtle, but look at the circle or the orbit and see how it's kind of flattening and getting more circular and flattening and getting more circular, okay? So hopefully you can see that. So that actually does change over millions of years or, even thousands of years, okay? Back to our PowerPoint. All right, so that's the first idea. Our next idea is going to be obliquity. So this is describing how tilted is the Earth. So hopefully you guys have learned in school already that the Earth's axis is indeed tilted, and that tilt is why we have seasons, okay? So think about it. We are in the northern hemisphere here in Ohio. So in the summer, we're just warmer overall because we're just spending more time facing the sun during the June and the summer solstice. Versus in the winter, it's colder overall because we're just spending more time away from the sun, facing away from the sun into space. And so this is what gives us seasons. It doesn't matter really how far or close you are to the sun. You still, as long as you have a tilt, you still have seasons, right? So that tilt can, again, also change over time. The most it tends to tilt is 24.5 degrees. The less it tilts is 22.1 degrees. And again, that kind of cycles. So it'll start off at 24.5, tilt less, and go back to more tilted every 41,000 years, okay? And so this is important because the more tilt you have, basically the more difference between summers and winters you have more seasonality. So if you think about it in terms of the poles, if you have very little tilt, if it's pretty up and, as close to up and down as you're going to get at 22.1 degrees, that means that, think about the North Pole, the difference between summer and winter temperatures is not going to be that big, which means that probably in the summer, it won't get that much warmer than it does in the winter, which means the ice will probably stay frozen, okay? Versus if you have more tilt, that's a bigger difference, again, the North Pole between the summers and the winters, which means in the summers, it's a bigger difference. It's probably going to be more warm than it was in the winter, which is a greater chance that ice will melt, okay? So that's an important idea to keep in mind for the lab and just in general. So the tilt can definitely affect, again, the seasons, how intense they are, and how likely it is that ice will either stay frozen or will melt in the summer, okay? So again, we will look at with our website to kind of illustrate this. So let's do that. Let's do tilt now. I'm going to do oblique view to see it a little bit better. So you can go back in time and you can see how, it's kind of subtle, but you can see how our tilt has changed over time. It's kind of wiggling like that, okay? So like that, yeah, there we go. You can kind of see it there, okay? All right. So then we have our third and final idea, which is precession. So precession is describing the wobble of the Earth as it spins. So I'm going to go right back actually to our website because otherwise it's hard to explain without a visual. So let's get rid of tilt. Let's do precession. Okay. So if you go back in time, you can actually see that the Earth wobbles as it spins. It's kind of like a top, where as it goes, it kind of will wobble back and forth. All right. And there's like really good videos out there that will show this a little bit cleaner than this does. So what this is really important to think about, because you can see like as it wobbles, the direction that the axis points, the direction that, like for example, the North Pole points will change over time, which is an important idea because, let's go back to our thing here. Okay, so what can happen is like, so right now with precession, our axis is pointed toward Polaris, which is our North Star. But with precession, it will over time wobble. And so 13,000 years ago, actually our North Star was Vega, a different star, because again, the axis was just pointed in a different direction. And what's important here to know is that you can be in the exact same, time of year, the same distance from the sun, but you're actually pointing in opposite directions. So here, the North Pole is pointing away from the sun at this time in the season. And here, the North Pole is pointing toward the sun at this time. So as you can see, like precession actually does have a big impact on like how much sun or radiance the Earth is getting at a certain point in time. Okay, so, and again, that wobble is completing every about 19,000 to 26,000 years. All right, so putting it all together, the combination of eccentricity, obliquity, and precession creates something we call the Milankovitch cycles. This is named after a guy who did a lot of math to think about how these factors might influence climate. But basically what we're saying is that, the Milankovitch cycles will describe, these warmer and cooler time periods, and it can describe how much radiation hits the poles, which again is a really key thing to influence overall climate. So back to our figure one more time to kind of show how this happens. Okay, so here's this one I set up differently. All right, so here, look over here at this thing over here. This is temperature, so warmer over here, cooler over here. So we can see, first of all, look at this purple line, how it kind of goes up and down. Okay, again, it's not perfect. This is real life, this is a real planet. The data is not always ideal or like perfectly patterned, but hopefully you can see how there is a kind of an up and down to this. Here's a crest of temperature. Here's a warmer temperature, then cooler, then warmer. Is a little baby bump in here, but that's kind of what happens. But it's kind of up, down, down, and then up, and then down, and then up, then down, then up. So, again, it's not consistent all the time. There's, little weird things it does sometimes, but overall, that's the Milankovitch cycle. That's kind of that warmer and that cooler cycle. And so this warmer, cooler cycle is being influenced, again, by these three ideas of obliquity, precession, and eccentricity. So I have here to kind of help show this from the top view. So I have this frozen on summer solstice. Summer is the warmest time of the year, the longest days, the most sun on the northern hemisphere. Here, the North Pole gets the most sun. So basically, what can happen is these three things: eccentricity, precession, and tilt. They're each doing their own thing, but once in a while, they can, two or all three of them can just combine in a certain way that just prompts just a little bit more, warming at a pole or a little bit more cooling at a pole. Sometimes it creates less sunlight and sometimes it creates more sunlight, more radiance or less radiance. Okay. And so that it's kind of just coincidence, but sometimes it does line up. And then we end up with conditions that, push us more toward an ice house or more toward a greenhouse. Okay. So I'm going to do this. So here we are right now. Let's go to a point when it was pretty warm. Okay. So here we are. This is again our temperature. Here's a warm spot. look at this coincidence. This is interesting. So because of precession, at this point in Earth's history, our axis just happens to be pointing in that direction. Okay. And that lines up with, so that puts our summer solstice, our warmest time of the year, it times it so that it happens at the same time that it's really close to the sun. Okay. You can see here, this is close to the sun it's going to be versus like over here somewhere, right? That's just kind of how it turned out. But the effect is that the North Pole is going to get pretty warm, and that's probably going to help melt the ice in the summers, right? And so tilt is a little bit harder to kind of visualize here, but we think about it, if there was, a lesser tilt, basically less seasonality, a little bit more up and down, basically the difference, the summers wouldn't be as extreme compared to the winters. If there's a greater tilt, then the summers would be more extreme compared to the winters. So if you think about it, it's possible, if we think about why this was so hot right here, maybe it's because it was had summer because of the direction of the tilt of the axis with precession, happens to happen at the same time that it's really close to the sun because of eccentricity, which also happens to happen maybe at the same time there's maybe a high tilt, which means more intense summers, more intense seasons. Those could have all three happened at once to create this peak of heat that we see here. Okay. Other option to think about is when it gets colder. So here's a colder time. Again, we're down a little bit cold temperature. Look at this. The summer solstice, the warmest time of year, is now happening when we are a little bit further from the sun. Now the warmest it's going to get is not going to be as warm as it's going to get when it was over here at a different time of Earth's history. Okay. And again, maybe at this time, the tilt of the axis was a little bit less, which means that there's less seasonality, less of a difference between the winter and the summer temperatures. Okay. So I hope that all makes some sense. I will again include this website. You can play with this and hopefully help yourself understand this idea. Caveat, these ideas are not always perfectly aligned. It's oftentimes not extremes. Oftentimes it's like some combination of the three are going to create some like moderate temperature. But it's a big, broad enough pattern that it's worth it. Scientists have agreed that it's probably doing something to the climate, okay, and creating those warm and cool cycles that we observe in our past. All right, so I will also include videos you guys can watch if that helps you to understand this differently. If I'm not explaining it very well for you, that is fine. Hopefully, other people can explain it better with different videos. I will include those in Carmen. Okay, so that's Milankovitch cycles. That's just a figure you can look at too. All right. So that was one big factor for climate and how it might change. The other big factor for how climate might change is carbon. This one is probably more familiar to you guys. So as you might know, the more CO2 you get in the atmosphere, the more likely you're going to have a warmer climate because of something called the greenhouse effect. So basically, we have energy from the sun. Again, radiance is the key thing here. It's going to hit the earth. And if there's more CO2 in the atmosphere, then more of that radiance will get trapped in the atmosphere and keep us warmer. If there's less CO2 in the atmosphere, then more of it escapes back into space. Okay? So again, hopefully you guys have heard about this idea a couple times already. So again, more CO2 equals generally a warmer climate. Again, more CO2 is probably less chance of there being glaciers. If there's less CO2, probably there's glaciers somewhere on the poles. Okay? So in the past, volcanic degassing, basically volcanic eruptions, if you're seeing eruptions, there are all these plumes, there's all kind of gas and CO2 being spat out by these volcanoes. So that has always in the past of the Earth's history been a really big source of CO2. We've had other times where it's been super warm in our Earth's history. And again, geologists speculate there's probably due to volcanics, which creates the warming. But of course, in the modern day, we know that human activity is probably also contributing to the amount of CO2 in the atmosphere. Basically because, we have our oil and gas industries, and coal industries as well. Because when you're burning these energy sources, that's basically burning dead life material. Coal is dead plants. Oil is more or less just dead microorganisms. In any case, they all have a ton of carbon in them. So when you burn that and put it in the atmosphere, we're dumping a lot of carbon that had been trapped in the earth in the form of coals and oils. We're putting it in the atmosphere. We're increasing the CO2 in the atmosphere. That is thought and has been more or less proven to have been causing the warming we observe in the modern day. Okay, so this is a figure you will see in the lab again. This is basically showing how the amount of CO2 in the atmosphere is correlating with ice ages, with ice age cycles. So you'll be asked to like identify, if there's more CO2 in the atmosphere, it's probably warmer. Is it likely to have glaciers? Probably not. Versus when there's less CO2 in the atmosphere, it's a bit colder, probably there's glaciers. So that's the question you guys will have. And so we have this regular cycle. Again, it has its quirks, has its kind of moments, but it does have up and downs more or less regularly. And then when you get to the modern day, we see how the CO2 curve really spikes and starts really going way up really quickly, almost a vertical line. So that's one piece of evidence that we use to think like, oh, maybe humans putting out a bunch of CO2 in the atmosphere actually is contributing to climate change. So that is kind of the last section of the lab that you'll think about.